Now we want to talk about the chapter 3 contents and starting with neighborhood reconstruction methods. So one of the points of focus in this chapter is node embeddings. The idea is that when you look at a graph like this, and let's say you want to represent nodes by a low dimensional vector in a semantic space, such that when you consider this latent space or this semantic space here, you want to sort of encode both the structure and relationships and other associations with the node in this new representations in this latent space. For example, you might want to optimize the relationships in the embedding space such that the distances in the embedding space reflect upon the basically structure or relative positioning of the nodes in the original graph, which is, for example, on the left. Here we want to talk about first about the encoder-decoder perspective in representing the graphs. This picture from the book on page 30 actually demonstrates this very clearly. There are two key operations in an encoder-decoder approach in graph representation. The encoder approach is supposed to take each node and from that node reach a basically project it to a latent space and give us an embedding vector, which is a mathematical vector, a real valued vector. And then the decoder is supposed to take this embedding that belongs to one of the nodes in the graph and give us back basically information that can help in reconstructing the neighborhood around that node. So the encoder is a function that for every node that belongs to the set of nodes is going to basically, if you apply the encoder on it, is going to give you a mathematical vector, let's say of d dimensions. And most of the time in practice, it is a shallow embedding approach in which you're going to essentially have a matrix and you have like an embedding for each one of the nodes. Now in this chapter, which is more of a beginning and introductory chapter, this node embeddings and for the encoder part, the focus is on essentially the shallow embedding, which we just described. But, the encoder section can basically go beyond that, and more on that will be discussed in a chapter related to graph neural networks. That means doing some more complicated stuff and, for example, considering the local structuring, obtaining the embedding and things like that. Now, let's go back again. So we are talking about the encoder-decoder approach in representing the graphs. We mentioned that if you have a node in a graph, the idea is that we want to have the encoder that when you apply this on it, it'll map it to a ZU in a latent space or semantic space or whatever. Now, the operation of the encoder, in this case, we mentioned that we have shallow embedding. So we have an embedding for each one of the nodes. Now, the question is, how exactly is the decoder going to operate? Now, there are many ways the decoder can be defined. For example, the decoder can be, considering, so let's say you give the decoder the ZU. It can, for example, try to predict the row corresponding to node U in the adjacency matrix. It can try to, for example, predict the neighbors of this node within the set of nodes, which is kind of the same thing, and things like that. But one of the standard practices is to focus on similarity, meaning that you have the vector, the embedded vector of a node for node U, for example, and you have the embedded vector for node V, and you want to find how similar they are, so, non-negative R. And this would be essentially the domain and range of the decoder. So an instance would be, for example, that you want to have this to be sort of similar to the similarity of U and V. And this, for example, could be defined as whether or not there exists a edge between them, or other similarity methods that we discussed earlier regarding, for example, number of paths between them and such. So how to optimize or train something like that also depends on basically what you want to do. Most of the methodologies are based on the gradient descent based methodologies of optimization. So a loss can be defined for this based on the results of the network, which is the reconstruction or finding this similarity assessment between the nodes U and V and the target similarity assessment. And this loss here could be, in some cases, it could be mean squared error. It could be, for example, cross entropy in some cases, and so on. So it's basically just going to be a loss to assess how well the decoder is finding out this target similarity. The next part of our discussion is going through an overview of the encoder-decoder approach. Most of the methodologies here, basically all of them, follow the shallow encoding approach. So basically, there are several degrees of freedom. You have decoder function to basically select, you have the graph-based similarity measure, and the loss function you're going to use to define the original loss function, such as the one that we mentioned earlier. Some of these methods are going to be motivated by matrix factorization. We're going to see that they also have close theoretical connections to spectral clustering, as well as the random walk approaches that were originally inspired by natural language processing, but they also have close ties to spectral graph theory. Now let's go over the functions in some of these methods, and we'll go in more detail for some of them. But it's kind of important, kind of intuitive to kind of see what kinds of decoder functions or loss functions they have used. So we can see that the graph factor and GradRep and Hope have this decoder here. So they basically have the same thing. They have different constraints on the similarity measure, however. But all of these three have the same loss. Then there's deep walk. So by softmax here, I mean that for the deep walk, for example, the softmax of ZU, TZ, ZV, or inner product of ZU and V is going to be the exp of ZU, ZV, for example, the exp of similarity of these two, divided by the summation of, for all of the nodes in the graph, you're going to have exp of ZU and consider the similarity with them as well. So that's what I mean by softmax here. Now both of these two have this loss function. So speaking of the factorization-based approaches, it's worthy to note that one of the main representations of the graph, as we discussed, was the adjacency matrix, and the task of basically node representation or decoding local neighborhood structure and things like that can be seen to be very closely related to reconstruction of the entries of the adjacency matrix. kind of a generalized version of that. So assuming that we have some sort of a similarity or user-defined similarity between the nodes, again, the task would be kind of also similar to having a low-dimensional approximation of that captures the information. Now let's talk about the first one of these approaches, Laplacian Eigenmaps. Let's say you define the decoder between the embeddings of the node u and v like this. So essentially it's going to be the squared error of this two, or a squared difference. And then the loss function be this. So you can see the idea behind this loss is that when two nodes are very similar, this value goes high. So in order to minimize the loss, this decoder function, which is the geometric distance between the two, or Euclidean distance between the two, has to be minimized. Now, a lot of the more recent approaches use the dot product between the embedding of two nodes and basically use that as the decoder. And the assumption here is that the similarity between two nodes that basically has to do, for example, with the overlap between their local neighborhoods is somehow proportional to the dot product of their embeddings. We can see that similar concept is also has been used a lot in the context of unsupervised learning in computer vision, for instance. So the use of dot product, cosine similarity, and these types of distances or similarity measurements have been very common in the recent machine learning literature. A good example, basically three good examples, are first the graph factorization or GF approach, the GradRep approach in 2015, and HOPE on 2016. So all these three methods are inner product based decoders with the following mean squared loss. So again, the loss is for the two nodes u and v, the L2 distance between the similarity and the decoder. Now the main difference in them comes from how they define this S, U, and V. So this is the measure of similarity between the two nodes and somehow could be proportional, for example, to neighborhood overlap. In the graph factorization approach, the system is a little bit straightforward, so S is defined to be the adjacency matrix. So this is for the graph factorization approach. The other two, meaning GradRep and HOPE, have somehow a little bit different strategies. GradRep defines S based on the different powers of the adjacency matrix, and HOPE's approach is based on neighborhood overlap. Now these are all matrix factorization based approaches because matrix factorization and their corresponding algorithms can be used in order to help solving these problems. An example of this is that, again, if you consider the dot products, you can basically stack all of these ZUs that are d-dimensional vectors into a matrix Z, and Z would be a matrix with the number of nodes as its rows, and each row is going to be d-dimensional, so it's going to be basically, this is going to be like this. So this is going to be Z. And obviously, if you transpose Z and you do the multiplication, when you take Z, ZT, and IJ, you're going to have ZI, or UI, doesn't really matter. You're going to have the dot product here. So you can reformulate and basically rewrite the loss value as this. And the solution to that has to do with the low-dimensional factorization of the node-to-node similarity measure. So in the matrix factorization approaches, the idea is to kind of learn low-dimensional embeddings for nodes such that the learned embedding vectors approximate some sort of a deterministic measure and well-defined measure of similarity between the two nodes, such as what we see here. The next thing we want to talk about is the random walk embeddings. So in the previous section, we discussed the inner product based methodologies. And one key thing about those methods that we discussed before is that they all use deterministic measures of similarity between the nodes. Meaning that in this approach, S is going to be some sort of a polynomial function of the adjacency matrix, and then we want to have some sort of decoded version of them, for example the inner product, approximating the assigned similarity value between the two nodes. Now recently there have been a lot of works in using the inner product in order to basically apply it on stochastic measures of neighborhood overlap. So the question that these recent and innovative works are trying to respond to is that can we learn node embeddings, for instance, for node U and V, ZUs and ZVs, such that if two nodes are similar, meaning, for example, if the inner product of them is high, that basically means that they are likely to co-occur on short random walks over the graph. And the two main models that we're going to talk about are deep walk and node 2-vec. The first thing to note about them is that both of them use a shallow embedding approach and an inner product decoder. And what makes them different also has to do with how they define the similarity and neighborhood reconstruction. The goal in this approaches is to learn node representations ZUs such that if you consider this probability, meaning PGT VU, be the probability of visiting node V on a length t random walk path that starts from node U. So this is just a notation here. The objective is to basically kind of learn representations so that you be able to sort of mathematically reconstruct the random walk statistics happening on this graph. So the decoder is going to be defined like this, meaning that for node ZU and ZV, you have the inner product of ZU and ZV here, and then you basically do some sort of a softmax in this sense, meaning that you have the similarity of ZU with any node K considered in the denominator here, and on the denominator you have the X of ZUT ZV. And this is supposed to approximate the PGT of V conditioned on U. Note that T is usually defined to be in a range of 2 to 10. Now, one other key detail to note here is that this probability definition that you have here and this, in sense of a stochastic measure of similarity between two nodes is, first, it's not deterministic, it's stochastic, and second, it is asymmetric, so it is not symmetric. Now, here's how you basically train something like that. First, you define the decoder. So let's go over the decoder again. You have two representations, of course. You're going to feed it to the decoder, and it is going to be defined as you take ZU, ZV, and you compute the inner product of them. And you do this softmax sort of approach. And this gives you the decoder value. Now you randomly sample, so basically you sample random walks, generating basically, so you can start sampling random walks from starting from each node, and you can basically build this dataset D, meaning, for example, if you start from node U and you basically can sample UVs from this probability by basically doing a random walk starting from U. And then after building this data set, what you can do is that you can define this loss. So for each of these sampled U and Vs, you want this measure of similarity that you have approximated, you want this value to be high. Therefore, in order to define a loss, you need to minimize this, meaning you need to maximize this, which in turn means maximization of this. Now, one major problem with this approach is that on the denominator for this softmax part, you would have this order of complexity at least in order to make the computation, just to evaluate the value. And this is basically how to deal with this is the main difference between deep walk and node 2-vec. Now, deep walk uses hierarchical softmax to basically deal with this and uses binary tree structure to accelerate the computation, but Node2Vec uses a noise contrastive approach and basically, instead of like dealing with everything, uses negative sampling. One thing about these two approaches is that the Node2Vec also, so deep walk kind of randomly samples these random walks, but Node2Vec also provides this flexibility and the option to choose random walks that are more akin to breadth first search or DFS or depth first search. And also in the other domains of machine learning, we can see that the noise contrastive estimation has been a lot more in use than, for example, hierarchical softmax. The line approach, or larger scale information network embedding, which was introduced in 2015, is also a pretty interesting approach with some close theoretical ties to the Node2Vec and deep walk approach. In this case, you have two encoding decoding schemes. The first one has this decoder, this being the sigmoid function, meaning that you have 1 plus 1. Sorry. So this is going to be used in order to approximate this measure of similarity, the same as adjacency matrix. So this is the first scheme and kind of is a first order hop approximation. And the second one is going to be the same decoder as before, meaning that it's going to be defined as the softmax of inner products. And yeah, so this is going to be that. And KL divergence is going to be used in order to train that to encode the two-hop adjacency information. Therefore, it is also in some sense close to Node2Vec and deep walk. Now, one thing to note about the general random walk approach and the random walk idea is that there can be a lot of modifications to it, and each modification could end up leading to a contribution, such as, for example, proposing a random walk that skips over nodes and things like that. Now we want to talk about the relationship between the random walk methods and matrix factorization methods. So these two types of methods are pretty close to each other. And to see that, let's say first we define the following node-to-node similarity measure. So we have S, which is going to be the logarithm here Now let's see what exactly these are. So B here is a constant, and P is D minus 1A. Now, if we basically define this similarity measure, the embeddings learned from deep walk will satisfy this approximation. We can look into this component of the work. So for t from 1 to tpt, d minus 1. Again, this can be decomposed like this. So D is going to be a matrix of degrees, and so we're going to have U. For each one of these, we will have the eigenvalue diagonal. And this thing here is closely similar to this format, the unitary U and the diagonal matrix lambda, which was one of the Laplacian definitions, and therefore kind of indicates the close similarity or close theoretical ties of deep walk with the spectral clustering embeddings. With the difference that now deep walk has this degree of freedom T and kind of works with that to kind of tune the contribution of different eigenvalues to the outcome. There have also been works trying to kind of figure out some ties between these matrix factorization based methods and, for example, Node2Vec, which is this reference in the book. Now we want to talk about three main drawbacks of the shallow embedding, which was mainly the embedding that was used in the aforementioned methods. The first main problem with that is lack of parameter sharing. In this case, when you're using an encoder and considering the nodes, the lack of parameter sharing is going to make both from the statistical perspective and the computational perspective, the entire operation to be rendered inefficient. Because it has been shown in the literature, for example, with things such as convolutional neural networks on ImageNet, or on image recognition and tasks as such, we know that parameter sharing is a very effective form of regularization that actually helps a lot. But in this case, we sometimes have to deal with O cardinality of the set of nodes, which is going to make a lot of applications intractable. The second issue is that the shallow embedding doesn't really use the rich node features that a lot of datasets have. So that is also one of the main drawbacks. And the third, which the book mentions as the most important one, is the fact that these are inherently transductive. And when you have new nodes added to your graph, you cannot easily use these to kind of generate features for those, and a lot of different types of optimizations might be needed. So the main drawback would be that they are kind of useless in inductive applications where you have to deal with unseen nodes.